Power Electronics, presented by R. Shravanti, Department of Electrical and Electronics Engineering, DBS Institute of Technology. Okay, so today we are discussing on PE second unit. So second unit is AC to DC converter. So AC to DC converter, that is single phase and three phase control rectifier. Okay. So these are the contents. So in single phase and three phase AC to DC control converters. Okay, we have phase control techniques. That is single phase line commutator converter, bridge connection, half-wave control converter with R and RLE loads, derivation of average load, voltage, current, and some numerical problems, and semi-fully controlled converter, bridge connection with R and RLE load, and derivation of load, voltage, and current. Okay, and 3 pulse, 6 pulse converter, bridge connection, average load voltages. So effect of source inductor, both dual and single phase, both single phase and three phase converter. So these are the contents in second unit. Okay, so types of phase control rectifier. Okay, so phase control rectifier. So what is phase control rectifier means? To controlling a, so the phase control rectifier means by using a phase angle we can control the output voltage. So okay, so here by we want to regulating the output voltage by using this phase control technique rectifier. Okay, so in this phase control technique we have to we have to regulate the output voltage. Okay, so by using this phase control rectifier we have to regulating the output voltage. So that means we have to control the speed also. So actually the application of phase control rectifier will be to controlling a DC speed drives. Okay, so the phase control rectifiers are classified into two types based on the type of input power supply, and each kind includes semi, fully, and dual converter. Okay, so here types of rectifiers will be here single phase and three phase. So whenever we are giving a input to single phase, that is a single phase, and we are giving a input supply will be three phase, that will be three phase. Okay, so in three phase we have, so rectifiers will be classified as single phase and three phase. So in single phase we have another types, that is uncontrolled rectifier, off controlled rectifier, and fully controlled rectifier. And this uncontrolled rectifier will another classified into half wave and full wave. And this full wave will be classified as split supply and bridge supply. Okay. So split supply is also called as midpoint supply. Okay. So in three phase, okay, three phase we have uncontrolled rectifier, off control rectifier, and full control rectifier. So in uncontrolled rectifier we have half wave and full bridge rectifier will be there. In full control rectifier we have half wave and full bridge rectifier will be there. Okay, these are the classification of rectifier. Okay, so two types of classification will be there, that is single phase and three phase. So in single phase we have uncontrolled rectifier, half controlled rectifier, and fully controlled rectifier. This uncontrolled rectifier will be classified as half wave and full wave. And full wave will be again divided into split supply and bridge supply. Okay, so these three phase control rectifier are again classified into three types, that is uncontrolled rectifier, off controlled rectifier, and fully controlled rectifier. So this uncontrolled rectifier will again classified into half wave and full wave bridge rectifier. Okay, and full control rectifier is again classified into half wave rectifier and full bridge rectifier. Okay, so we have to see this operation of half wave converter with R and RL load. So half wave control rectifier will be uncontrolled rectifier. Okay, so this single phase half wave control rectifier, first you have to discuss R load. Okay, so as shown in figure below, the primary of transformer is connected to AC main supply with the SCR becomes a forward bias in positive half cycle. So T1 is triggered at an angle of alpha. T1 conduct the voltage applied across R. Okay. When you see this diagram, this is a single phase half wave rectifier with connecting R load. Okay. Here Vs equal to Vm sin omega t. Okay. Here we are giving a single phase. Okay. These are the single phase half wave rectifier with R load. So single phase AC supply, here we are giving. So AC supply means Vs equal to Vm into sin omega t. Okay, here this supply will be connected to thyristor T1. Okay, and this thyristor will be connected load, resistance load R. Okay, whenever we are giving a supply, this thyristor will be. So when thyristor will be turned on means by giving a triggering pulse, then thyristor will be turned on. Okay. So here this is the input supply. Okay. So the input supply will be sine wave. Okay. So whenever we are giving a gate triggering at alpha angle. Okay. So at alpha angle we are giving a triggering pulse. Then thyristor will be turned on and current flowing from thyristor to resistance load and okay, and again this comes to input. Okay, so this is VT. Okay, so this is a thyristor voltage. At starting, the thyristor voltage will be 0, and whenever we giving a triggering pulse at alpha, the thyristor voltage will be conducting state, and in negative side there will not conduct a thyristor. So negative side same supply voltage will be there. Okay, and we are giving, and after cycle, so at alpha the thyristor will comes to conducting. Okay, this is load voltage. Okay, so load voltage means when we are giving a triggering pulse, here the voltage will coming to high point and reducing to 0 at pi and at angle of pi. At angle of pi it will comes to 0. So it will comes to 0 at negative side, and after triggering this will be increasing. So this is a single phase half wave rectifier waveforms with RL load. So by using sine wave we are discussing the single phase half wave rectifier waveforms with R load. Okay. So the load current I0 flows through R. The waveforms for a voltage and current are shown above. So as the load resistance and output current is given by output current equal to V0 by R. Okay. Hence the shape of output current is same as the output voltage. As T1 conduct only in positive half cycle, as it is reversed bias in negative cycle. The ripple frequency output voltage is, so full frequency equal to 50 Hz, that is supply frequency. Okay, so average output voltage, we are calculating average output voltage. V not average equal to, here average voltage will be calculated by taking one by total time into integration of 0 to t, how much this will conducting that time into V naught omega t. Okay, area under the one cycle. Okay, therefore t equal to 2 pi and V naught omega t equal to Vm sin omega t from alpha to pi, and the rest of the period will be 0. Okay, here actually in this waveforms we are seeing, so we are calculating average voltage from 0 to 2 pi. Okay, so actually in the pi to 2 pi this will be 0. Okay, so the thyristor voltage will be 0. So that's why we are calculating from 0 to pi. Okay, the output voltage will be calculating from 0 to pi. Okay, so actually we are giving input voltage equal to Vm sin omega t. So 1 by 2 pi integral 0 to 2 pi Vm sin omega t. So here 0 to 2 pi will be divided into two parts, that is alpha to pi and pi to 2 pi. Here pi to 2 pi will be 0. So here alpha to pi. So sine omega t, integration of sine omega t means minus cos omega t. When you are taking a common Vm, so then Vm by 2 pi equal to minus cos of omega t alpha 2 pi. So Vm by 2 pi into, when you substituting this alpha and pi, starting minus cos pi means minus of minus 1. So that means plus 1 and plus cos alpha. Here we are taking a cos alpha. So average output voltage of half wave rectifier will be Vm by 2 pi 1 plus cos alpha. So this is average output voltage of half wave rectifier. Next we are calculating the RMS load voltage. VRMS equal to 1 by T integration of 0 to T Vm square sine square omega T and d omega T. Okay. So that means VRMS equal to 1 by T means here time period will be 2 pi and 0 to T. Here 0 to T, this we are calculating alpha to pi. Okay. So pi to 2 pi will be 0. So then we are alpha to pi Vm square sine square omega T d omega T whole power 1 by 2. So actually RMS voltage we are calculating 1 by 2. So VRMS equal to, where when you taking a common Vm square, then it will come outside, then it will become Vm by 2 pi and integration of Vm sine square omega t. So sine square omega t means okay, here integration of sine square omega t. Sine square omega t means 2 sine omega t. Okay, 2 sine omega t and plus sine omega t means, so plus sine omega t we are calculating. So then substituting this alpha to pi, so sine omega, sine pi, so sine pi minus sine alpha, okay, plus 1 by 2 sine 2 alpha whole power 1 by 2. Okay, this is VRMS. So VRMS equal to Vm by 2 root pi minus alpha plus 1 by 2 sine 2 alpha. So when you substituting, if alpha equal to 0, here alpha equal to 0 and VRMS equal to Vm by 2. Okay, so if alpha equal to 0, then VRMS equal to Vm by 2. Okay. Next. So input volt ampere. Okay. So input volt ampere equal to RMS source voltage into RMS line current. RMS source voltage means Vs and RMS line current means IRMS. Okay. So Vs into IRMS means, so VRMS by, so VRMS by so this VRMS dividing by resistance, then it will be IRMS. Okay. So same root 2 Vs by R into 2 root pi into pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2. Then Vs square equal to root of 2 pi into R pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2. This is input volt ampere. And input power factor, it is defined as the ratio of total mean input power to the total RMS input volt ampere. So input power factor will be mean input power by, so mean input power by input volt ampere. This is input volt ampere and mean, so root 2 Vs by 2 root pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2 by Vs. So 1 by root 2 pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2. By simplifying this, we get input power factor will be 1 by root 2 pi minus alpha plus 1 by 2 sine 2 alpha whole power 1 by 2. Next, form factor. Form factor is defined as the ratio of RMS voltage to average voltage. So form factor equal to VRMS by V average. So effective value of AC component, the output voltage equal to VAC equal to VRMS square minus V average square whole power 1 by 2. And ripple factor. So ripple factor is defined as the ratio of AC component to the DC. So where the ripple is the amount of AC component present in the DC component. Okay, RF equal to VAC into V average. VAC means VRMS square minus V average square whole power 1 by 2 by V average. So that means VRMS square, VRMS by V average whole square minus 1 whole power 1 by 2. That means VRMS by V average means form factor. So form factor square minus 1. So this is root. Okay. This is ripple factor for half wave rectifier. And transformer utilization factor. So it is defined as the ratio of output DC power to the volt ampere rating of transformer. Okay, so output DC power by volt ampere rating of secondary winding of the transformer. Okay, rectifier efficiency. It is defined as the ratio of output DC power to the input AC power. Okay, so rectifier actually efficiency means output power by input power. Same V average by, actually here output will be V average and input will be VRMS. So peak inverse voltage PIV means, so it is defined as the maximum voltage that SCR can be subjected to the reverse bias condition. So in a half wave case it will be VM. So PIV will be VM in a half wave. Okay. So here P naught, P average, power, output power V average equal to V average square by R. Thus the power and voltage can be controlled by a firing angle. Okay. Next, single phase half wave rectifier with RL load. In the above case, we discussed single phase half wave rectifier with R load. But here we are connecting inductance, combination of resistance and inductance. So this AC supply will connected to thyristor, and this thyristor will be connected load of resistance and inductor. Here we are taking a sine wave as a input. So whenever giving a supply firing angle at alpha, when you triggered a thyristor, so this is a triggering pulse. So when I am giving this triggering pulse at alpha, so so here the voltage will be obtained. So source voltage will be at before triggering, the source voltage will be higher, and after triggering of SCR the source voltage comes to 0. In negative side the source voltage will be same as input, and it will be comes to 0, and after completing one cycle it will be going on increasing and comes to 0. This is a source voltage. And this is a thyristor voltage. Okay, so thyristor voltage VT is that means output voltage equal to at a triggering of thyristor, the load voltage will increasing, and it will comes to 0 at 5, and in reverse bias it will commute sometime due to because of inductor, it will commute sometime and it will comes to 0. Okay, and in reverse bias the load voltage will comes to 0, and after completing a cycle 2 pi it will at triggering of alpha, then again the load voltage will again increasing, and it will be decreasing at 2 pi in reverse, and it will not the SCR will not be turned off when cycle will be 0. Why? Because it commutating. So when it will commutate, so due to inductor it will commutate. So here the inductor, due to commutation of inductor, here the voltage in negative cycle will be there. Okay, and it comes to at some angle. Okay, at some angle it will comes to 0. And here load current. So load current will be starting 0, and by giving a firing angle it will be increasing and decreasing at so here it will be decreasing at 5 plus alpha, and comes to 0 in negative cycle, and it will be increasing at 2 pi plus alpha. Okay, so this is a half wave rectifier with half wave controlled rectifier with RL load. This is the circuit diagram and this is their waveforms. When you seeing this operation, and the figure above shows the single phase half wave rectifier with R load. Normally motor are a inductive load. So L is the armature or field coil inductance, R is the resistance coil. In a positive half cycle, SCR start conducting at a firing angle alpha. So drop across SCR is small and neglected. So output voltage is equal to supply voltage. Due to RL load, the current through SCR increases slowly. At 5, supply voltage is at 0. So at 5, the supply voltage comes to 0, where the load current is at its a maximum value. So at 5, the voltage will comes to 0, but load current is at maximum value. In positive half cycle, the inductor stores energy and that generate the voltage. Okay, so this is a inducting generating voltage at after completion of angle phi. So this is the in the voltage will not be comes to 0 due to because of inductor. Okay. So in negative half cycle, the voltage developed across the inductor forward bias SCR and maintain its conduction. Basically, it's a property of inductance. It opposes the change in current. Basically, with the property of inductance, it opposes the change in the current. Output current and supply current flows in the same loop. Okay, so output current and supply current flows in the same loop. So all time I naught equal to IS. Okay. After pi, the energy of inductor is given to main and there is a flow of I naught and energy is reduced as it gets. So consumed by the circuit. So the current is also reduces. At beta, energy is stored and inductance is finished. Hence I naught becomes 0 and T1 is turned off. I naught becomes 0 from beta. So from beta to pi 2 pi plus alpha. Hence it is a discontinuous conduction mode. Okay. So in this waveforms we have to see here from 5 it will comes to 0 and here some amount of due to inductance some amount of voltage will be there and current also will be there. Okay. So here this is the inducting story. So at beta, so when you're taking this beta, it's so from pi to beta or 2 pi to beta. Okay, this is the inductance inductance conduction state. Okay. So when you're taking a VDS, okay, output voltage Vm equal to Vm by 2 pi into alpha to beta. Okay, sin omega t d omega t equal to Vm by 2 pi cos alpha minus cos beta and VRMS. VRMS equal, actually here alpha means firing angle. So the SCR firing angle will be alpha and beta will be extension angle. Here RMS load voltage equal to root of 1 by 2 pi alpha to beta Vm into sin omega t whole square d omega t. Okay. So VRMS equal to root of Vm square by 2 pi alpha to beta sin square omega t d omega t and root of Vm square by 2 pi integration of alpha to beta means so 1 by 2 into 1 minus cos 2 omega t. So sin square omega t means 1 by 2 1 minus cos 2 omega t d omega t. Okay, Vm square by 2 pi 1 by 2 and here we are substituting omega t and 1 by 2 sin 2 omega t. So Vm square by 2 pi 1 by 2 here we are substituting alpha and beta. So then beta minus alpha minus 1 by 2 sin 2 beta minus sin 2 alpha. So plus Vm by 2 root 2 pi and simplifying this beta minus alpha minus 1 by 2 sin 2 beta minus sin 2 alpha. Okay. So this is a VRMS voltage. This is Vm by 2 root 2 pi beta minus alpha 1 by 2 sin 2 beta minus sin 2 alpha. Okay. So the average load current can be obtained. So by dividing the average load current, the average load voltage by the load resistance. So here IDC equal to Vm by 2 pi r cos alpha minus cos beta. So L into di by dt plus R into I equal to Vm by sin omega. So in this from circuit diagram of inductor. So from this circuit diagram of half-wave rectifier with RL load, L into di by dt plus I into R. So L into di by dt, I into R equal to Vm sin omega t. Okay, Vm sin omega t into alpha less than or equal to omega t less than or equal to beta. Okay, so di by dt plus R by L into I equal to Vm by L sin omega t. Here by dividing with L, so di by dt plus R by L into I equal to Vm by L sin omega t. Then I of omega t equal to e power of minus R by L t and integration of e power R by L of t into Vm by L sin omega t d omega t plus k. Here, so I omega t we are calculating. So Vm square by R square plus omega square plus L square into R sin omega t minus omega L cos omega t into A into e power minus R by L t. Okay. Here R equal to Z cos phi and omega L equal to Z sin phi and tan phi equal to omega L by R. Okay. So I omega t equal to Vm by Z cos omega t sin omega t and we are substituting these. So sin phi cos omega t plus A into e power of minus omega t tan phi. Okay. Then I of omega t equal to Vm by Z sin of. So what is the formula means? Sin of A minus B. Here sin omega t minus pi plus A into e power of minus omega t by tan phi. Okay. Here high alpha equal to 0. Then here A equal to minus sin of alpha minus beta. So then I of omega t equal to Vm by Z sin omega t minus pi. Okay, sin omega t minus pi and sin of alpha minus pi into e power minus omega t minus alpha by omega L by R. So with the limits of alpha less than omega t and less than beta. Okay. So single phase software rectifier with R load and RL load we are discussed about, and now we are discussing single phase half wave controlled converter with RLE load. Okay, so the diode D2 and D4. So this is a single phase half wave controlled converter with RLE load. Okay. So here this is in the about T1 and T2 and here D1 and D2 will be there. Okay. So here resistance, inductor and E, battery E will be there. Okay. At starting when are giving a supply T1 and T1, T2 and D1, D2. Here T1, D2. T1, D2 will conduct and T1 and T2 here T1 D2 and T2 D1 will be conducting. Okay, so in forward in positive half cycle T1 D1 will conducting and in negative half cycle this T2 and D1 will be conducting. So when you taking this T1 and this is T2 and we are taking this D1 and D2. Okay, then T1 D1 and T2 D2. Okay, so this is when you see these waveforms. Okay, when you see these waveforms, this is a so input will be sine wave. Okay, so at starting this T1. Okay, these are the conducting states of T2 at starting this T2 D2 will be conducting. After that T1 D1 will be conducting. Okay, here the load voltage will be so the load voltage will not be 0. It will be straight line. Why? Because here we have resistance, inductance and battery will be there. And here we have T1 D1 and so in positive and negative half cycle the current will be will not be 0. It will be going on straight forward. And output voltage will be at alpha. So when triggering of this thyristor at alpha, it will be the output voltage will becomes, and it will becomes to 0 at pi minus alpha. Okay, and it will and again it will be at pi plus alpha. It will be again increasing. So this is VD1. So this is a input voltage. So the diode voltage VD1 voltage will be like this. So and it will be here VD2 will be higher. Uptime in negative cycles will be at pi plus alpha. After at pi plus alpha, the VD2 in negative half cycle will be obtained. Okay, this is single phase half control rectifier with RLE load. Okay, this means the diode D2 and D4 conduct for positive and negative half cycle. The input voltage waveforms respectively on the other hand, T1 start conduction when it is fired a positive half cycle. The input voltage waveforms is a continuous conduction till 3 is fired a negative half cycle. So figure shows a circuit waveforms of single phase half control converter supplying RLE load. Okay. So referring it to a figure, this T1, D2 start conducting at omega t equal to alpha. So the output voltage during this period becomes equal to, so at omega 2 equal to pi, as a tends to negative D4 is a forward bias and a load current commuted from D2 to D4 and free wheels through a D4 to D1. Okay, so the output voltage remain clamped to 0 till 3 is are fired at omega t equal to pi plus alpha. The T3 and D4 conduction mode continues up to omega t equal to 2 pi, where upon the load current again free wheels through T3 D2. Okay, while the load voltage is clamped, okay, while the load voltage will be clamped to 0, from this continues in the previous paragraph, it can be concluded that output voltage, okay, hence the output voltage in periodic over half of the input cycle, hence V average equal to 1 by pi integral 0 to pi V naught into d omega t. Okay, here equal to 1 pi pi into alpha 2 pi root 2 vi sin omega t. So that means root 2 v by pi 1 plus cos alpha. Okay. So I naught equal to v naught. Here we have in load we have E will be there. So v naught minus E by R. Okay. So root 2 vi by pi R 1 plus cos alpha minus pi sin theta. This is a I naught value and this is a V naught value. Okay. Okay. So today, thank you for this. Today we discussed half wave rectifier with RL load and RLE load. Okay.